Now, turn the mic on. There we go. All right. You know, it never said the recording stopped. I don't know. But it's 3:01. We should be good. Okay. All right. So then in terms of CTP, which is what we're going to be looking at now. Let's see, we've got to go back. This thing's got jumped around here. All right. So we looked then at the connective tissue family and the fact that some of these cells then are interchangeable. And this has been shown from the stem cell studies, which we're going to be talking about toward the end of the lecture. But these cells then are designated as the support cells of connective tissue, whether we're dealing with a specialized connective tissue like bone or adipose tissue, or the connective tissue proper, which is what's filling in the gaps all over the place. All of these cells are derived from an embryonic tissue called mesenchyme, and they are noted for producing a variety of extracellular materials. So we will look at, we've seen some a little bit in terms of the synthesis of collagen. There are other fibers that are going to be produced. There's ground substance that gets produced. They produce materials like hyaline cartilage, fibrocartilage, elastic cartilage coming from the chondrocytes, bone, and fat, right? So a number of extracellular materials. But think about it. All of these are structural supporting kinds of tissues. They adhere to the extracellular matrix components that they've produced rather than to other cells. Fibroblasts do not make junctions with other fibroblasts. Chondrocytes don't make junctions with other chondrocytes, although they can be in little nests. The exception are the adipocytes, okay? Fat cells are a very different kind of tissue in that they have very little matrix. Unfortunately, they take up the space with storage of fat. And so where other cells have made matrix around themselves, adipocytes fill themselves up with fat. The major component of connective tissue is the matrix, whereas in epithelial tissues, the major component were the cells, right? Virtually no intracellular matrix. And then the cells are sparsely located in the extracellular matrix. In some cases, in cartilage or in bone, they take up very specific locations within it. But that's for another day and a different lecturer. Okay, and before we get into CTP, let's look at the two embryonic tissues, mesenchyme and mucous connective tissue. Mesenchyme, then, is the embryonic tissue from which all of these other cells come, right? And so this is where, these are the stem cells. And they're spindly shaped cells. They have a fair amount of matrix between them. They're found within the mesodermal disc of that trilaminar disc. And they do, at this stage, communicate with other cells through fine cell processes. In terms of the mucous connective tissue is something that is embryonic. It is called Wharton's jelly, okay? They are one and the same, Wharton's jelly being the eponym name for it. And these cells are also a source of stem cells. They are found around blood vessels within the embryo or in the fetus, and particularly they are found around the major umbilical vessels connecting the fetus to the placenta, which we'll look at the next to last lecture in the class. These are stem cells, so Google it and you will see that there are all kinds of umbilical cord blood banks now so that you can save your child's stem cells. Also, hospitals, researchers would love to get a hold of them also, okay? Could you sign away your umbilical cord? That's because of these stem cells that are here and their pluripotential within this mucous connective tissue, all right? So very spindly shaped cells, not as populous in terms of cells, numbers of cells, as the mesenchyme. And once again, mesenchyme will still be around, whereas these mucous cells are pretty much only in the embryo and around blood vessels. Okay, that's it for embryonic tissue. Now let's get into connective tissues themselves and their extracellular matrix, okay? All right, so they're going to be derived from mesenchyme, mostly from mesoderm. I'm saying mostly from mesoderm because if you go back to that very first slide, all the way back at the beginning of the epithelium lecture, I mentioned that there were some mesenchymal cells from the head region that come from neuroectoderm. But that's going to be very specific. It deals with branchial arches, et cetera, and you're going to just love to hear Dr. Eliska tell you all about that come the winter term, okay? So don't worry about it until then. They have few cells, abundant intercellular space, and ground substance with any number of different fibers within it. They are vascularized, meaning they do have a blood supply. In fact, these connective tissues are the route through which the blood vessels are going to get to the various regions of the body, okay? They contribute to the basal lamina in terms of anchoring fibers that come up from the connective tissues, and they support the other tissues and organs, okay? And in fact, when you start to get diseases which affect some of these fibers, you could have things like double joints, etc. Okay. Now, they get classified in a number of ways. The two most common, let's forget about all those special tissues that we talked about, including fat, okay? The two most common ones and most prevalent, unfortunately fat gets prevalent to a certain extent too, it's not always good, are the dense, irregular, and loose connective tissues. And these tissues basically have the components of collagen fibers, fibroblasts, which are going to make the fibers, and maybe some of the other, a few other fibers in it, and ground substance between the collagen and the fibroblasts. Now, this particular, these two particular micrographs, it's just a high and low power view, okay, the same thing, are from the mammary gland. Loose connective tissues, first of all, dense connective tissues add stability, and they add a lot of support to tissues. In this case, dense connective tissues adding support to the breast. Okay? The loose connective tissues are found mostly right up under the epithelium, where there generally is a capillary bed of some sort to feed that epithelium, on around blood vessels, okay, for movement. Now, this is from the mammary gland, and as we'll see when we look at this in about 3 weeks, these are secretory units that are going to change. They're going to change with the stage in a woman's life. They're going to change with the stage within a menstrual cycle. They're going to change with pregnancy, right? And the loose connective tissue immediately around these secretory structures allows for movement and expansion of these secretory units. And then the denser tissue around it adds for the support of the breast material. And then there's always a fair amount of fat in the breast, adipose tissue. So dense, irregular, and loose connective tissue. The fibers appear to not take any particular direction. However, they actually do, particularly in the skin and in the dermis of the skin, where they form stress lines for incisions called Langer's lines, Langers. So surgeons will follow the direction of fibers for stress, to follow the lines of stress so that the wounds will not pull apart. Okay? They'll go with the fibers parallel to them as opposed to perpendicular to them, if it is possible. Sometimes you can't do that. Okay? Okay, so the fibroblast. This is the workhorse, okay? This is the cell that does all of the work. It makes all the fibers. It makes, within connective tissue proper now, it makes all of these matrix factors. It is an extremely active cell, and when you see it, it is usually a very long, spindly shaped cell because it is lying there within all of the collagen fibrils that it's made, right? So two different views of it, and here you can see that we have a cell that has a very, very active euchromatic cytoplasm, prominent nucleoli, more than one, and a lot of RER. It's making a lot of protein, right? Okay? So, and here on light microscopy, this is actually taken from a very regular kind of connective tissue we'll talk about at the end. This is not irregular. These fibers are very straight. These very skinny, straight, purple areas are the fibroblasts, the nuclei of the fibroblasts as they are there embedded within these collagen fibrils. Okay, so this is the workhorse of the connective tissue. So it's going to make all the fibers, and then it also is going to make the matrix around itself and in between those fibers. And now that extra cellular matrix will consist of ground substance, and this is a hydrated gel. It's very important. It's made up of some very large molecules called glycosaminoglycans, some proteoglycans, some adhesive proteins. And hydrated, there is within that ground substance a large molecule called, it's a repetitive chain of disaccharides that retains water, that binds water to hydrate this gel. And that gel gives to tissues a property called turgor, tissue turgor, swelling or fullness, so that if you have, in many elderly patients who don't have a proper diet, or somebody who possibly has had food poisoning and had all those little zonula occludens junctions broken down and diarrhea and has lost a lot of their fluids and is dehydrated. If you grab the skin, it doesn't bounce back. All right, but if you have tissue turgor and you have a lot of, you have fullness in that tissue, then you get a bounce back, okay? So I don't have any of those things right now. I am not dehydrated. I've been drinking. Okay. All right, the other thing that's then embedded then within that ground substance are going to be fibrous proteins, fibrils. Collagen, which we saw, of which there are many types. Type 1 is the one we're going to deal with today, plus another finer one called a reticular fiber, collagen 3. Fibrillin and elastin, which are part of the elastic fibers. They help to give recoil to tissues. Fibronectin. Fibronectin is very important in wound healing, okay? And it's also important in terms of adhesion to the basal lamina. And all of these help to give anchorage for all the elements that are within the cells, within that tissue, and then, of course, they give tensile strength, particularly the collagens. So these fibers then are embedded in the ground substance, and this is a gold casting of a proteoglycan aggregate in the extracellular matrix. And this may look something like something very similar to what Dr. Arch showed you, I think, in the second lecture or the first lecture on microscopy. But in that case, yes, there were all these cute little spokes coming off of a main stem, but it was shaped like a Christmas tree, and he was showing, I think, RNA synthesis. Okay? So don't confuse the two. All right. So this then is, these are fibers in the ground substance, and this is that same scanning that we saw before of the fibroblasts with those fibers around it. At this level, I couldn't tell you if these were collagen or reticular or elastin. They may be a whole mixture of several of them. But the dark spaces in between are the ground substance where that hydrated gel would be located, okay? Where you would get that tissue fullness or a turgor. So in terms then of that proteoglycan molecule, you've got the hyaluronidan with the glycosaminoglycans and the proteoglycan monomers that are going to fill the gaps and spaces between the fibers within them. And it is that hyaluronidan molecule here which is the one that is going to be binding all of that water and holding on to that water and to help for deposition of collagen within these tissues. Collagen itself, in terms of its synthesis, is very important because it does give strength to these tissues, tensile strength. It also is important in wound healing and in bone formation. A collagen matrix will be laid down during bone formation. And for wound healing, this will be part of the scaffolding for deposition when scar tissue is being formed to close wounds. Vitamin C is a very important cofactor for the synthesis of collagen for hydroxylation in its processing, and wound healing is impaired greatly. Bone formation is impaired greatly in scurvy. Scurvy? Know what scurvy is? Huh? People don't get enough vitamin C? Okay. All right. So, also there are some metalloproteinases that help to degrade collagen and to keep the turnover going, to keep it maintained at a certain level within the tissues, and that too is important in terms of scar formation and wound healing and for tissue remodeling. Okay. The other type of fiber is the elastic fiber. Now, collagen are the ones, H&E, we see those, right? They pop right up when we're looking at CTP and H&E. Elastic fibers are harder to distinguish on H&E. They're smaller than collagen. They contain a couple of different very special amino acids called desmosine and isodesmosine. They have the ability to recoil so that when a tissue is stretched or for whatever reason, it can come back to its original shape. So the fibers are wrapped around with another protein called fibrillin, a smaller protein that helps to bind them into these aggregate bundles. Now there's a defect in fibrillin processing, in the fibrillin gene, which causes a condition called Marfan's syndrome. So people have hyperextensibility of the joints, they have elongation of the bones, very tall, and they also have, as you'll see, because the aorta is one of and the other large blood vessels have a lot of elastic in their walls, mixed in with their smooth muscle, that it can cause disruption within the aortic walls and disruption and bulging and then eventually aneurysms that can burst, right? So that's Marfan syndrome, and it's caused by the fibrillin defect, a mutation of the fibrillin gene that causes a defect in this protein and prevents all this bundling. The elastic fibers aren't that easy to see. And here we go with those special stains, okay? They need to have a special stain. To a certain extent, you can kind of say, okay, yeah, that skinny little fiber there on an H&E is an elastic fiber. But if you see that you have a Verhoef stain or a Weigert stain, use those as guidelines that you are looking at elastic fibers, and in both cases, they appear very dark and thin, okay, and branching. They branch a lot, and in here there are these very thin, dark fibers, whereas the collagen is appearing as a very lightly stained, thick fiber here, and also fairly light in here. They don't show up very well. The rest of these structures are blood vessels. This loose connective tissue has actually been taken from a mesentery, that is one of the coverings of the abdominal organs, right? That consists of a very thin layer of epithelium with connective tissue underneath. Okay, third fiber, reticular fibers. Different kind of collagen now, okay? Collagen 3. This type of collagen has a lot more sugar in it than collagen 1, than the normal one. These are very fine fibers. They can be found in the region of the basal lamina for attachment. They are found around adipocytes, it's fat cells, blood vessels, nerves, nerve fibers. They are also involved in wound healing and scar formation, adding support. And in addition to fibroblasts, they get made by the Schwann cells, which are the peripheral nerve system supporting cells, smooth muscle cells, and reticular cells, which are found in lymph nodes. So you'll be hearing about all of these again in future lectures. Because they have a lot of sugar and they're very thin, fine fibers, they're called reticular because they form like a reticulum, a network within organs. They are the basis in lymph nodes, and they're found in the liver. They can be stained with things that will stain sugars. So what could stain these then that we... PAS. Good. All right. Also silver. Silver will also stain sugars. So those two things, okay? So silver stains and PAS can stain these cells. Okay. In terms of the cells themselves, we break them down into resident cells, those that are almost always within the connective tissue. They're there, they live there, or those that are passing through. For the most part, if you look at these are all the blood cells Dr. Becker was talking about, right? And plus, well, lymphocytes and plasma cells, he'll be talking about those a little bit more, probably in the lymphoid lecture. But fibroblasts, they're there. Macrophages are there. The adipocytes, not only do they make their own special adipose tissues, they are there within other connective tissues, the connective tissue proper. Find them in the dermis, find them around other cells, mast cells, and the mesenchymal stem cells. Yes, there are stem cells there lurking around. In fact, almost all the tissues have some stem cells lurking around. The fibroblasts, then, this is in dense, irregular connective tissue, collagen. So here, remember, they're just going to look like very small, spindly cells in between the fibers. And somewhere within this population of fibroblasts, there is a small population of cells called myo, M-Y-O. That was my pop bottle. Myofibroblasts. Pertaining to muscle for movement. And these myofibroblasts have contractile properties very similar to smooth muscle. They're very important in wound healing. You're hearing a lot about wound healing now, aren't you? Okay. They're really important in wound healing, and this population gets activated in wound healing to, one, help to migrate in, to help to close up the area, and then when there actually is closure of the wound, it is the myofibroblasts that migrate to close that wound up, okay? So myofibroblasts, there are probably a certain number there, and then because it can change properties, the fibroblast itself can take on some of these characteristics, and some of those may also differentiate during wound healing. So we've seen this before. Here's that fibroblast, remember it, with its very prominent nucleolus and its primary cilium, little basal body there, huh? Okay, and this is basically going to be some sort of a sensory receptor for this cell. Lots of mitochondria and RAR. The macrophages, okay, sometimes called tissue histiocytes. They can be difficult to identify, and generally, unless you see some that have vacuoles in them within the tissue, here's one here, they are pretty difficult to identify as macrophages. They're phagocytic. They likewise are going to be very, very active in wound healing. In fact, when there is an injury, macrophages are one of the first guys on the block to come on in and to start picking up stuff and to start releasing growth factors and cytokines to get the rest of the cells in. So they're involved in inflammatory responses, immune responses, and they have the ability to move through the ground substance, and they do that by using a glycosaminoglycase, right, to break down some of those ground substance proteins. Mast cells are involved in hypersensitivity reactions, and generally they appear either very blue, or they can also appear like very red granules. The difference between these and the eosinophil is that they do not have a bilobe nucleus, and you generally can see their nucleus, right? Whereas with the eosinophil, the whole thing sort of looks like it's covered up with cells. They're also larger. And then our friend, the plasma cell. This is from Dr. Rogowski's lecture, huh? And she used this particular slide to talk about the Golgi, right, and the placement. So we're still going to use it because that clear space, which is the location of the Golgi, the paranuclear space there, clear space is one of the characteristics of these plasma cells. They're derived from B lymphocytes, and they are antibody-producing cells. They don't have a very extensive migration area, but they do get there when they are needed, and they have, because they're antibody producing, they're making proteins, and they have those properties of a cell that is making proteins, meaning a prominent Golgi and a very prominent, extensive RER network. So the bulk of the cell is filled with with the rough endoplasmic reticulum, and the area near the Golgi, near the nucleus where the Golgi is located, appears as a clear area on both light and in electron micrographs. The nucleus is always eccentric, that is off to one side, and it has what's called a clock face nucleus. So we have clumping of the chromatin around the outer edges of the nucleus. Those are very characteristic of plasma cells. You're going to find them in many areas of the body, particularly in those areas where there's openings to the outside. So in the urinary tract, in the mammary gland, GI tract, you'll find them. That isn't to say they're not anywhere else, but expect to find them in those regions. And then in terms of, so that's CTP, and in addition then, the collagen fibers can take a much more regular kind of binding pattern. And in this case, they are lined up with the fibroblasts that have made them in between, and they're in parallel arrays. And this could be either a ligament connecting bone to bone, or a tendon connecting muscle to bone. In both cases, we're dealing with type 1 collagen. In the case of the tendon, it's being formed from the coverings of the muscle fibers itself. As the muscle fibers, the muscle bundles, and then finally that entire muscle and all the connective tissue coverings that are around it, what you will know and love as deep fascia, will come in and form this very nice tight tendon. In the ligament, there will also be some elastic fibers in here for the movement of the bones. Once again, here's that loose connective stain. Just to remind you, loose connective tissues are going to be around the blood vessels, et cetera. How are we doing here? Oh, 3:30. All right. Okay, so any questions on CTP? Nope? Okay, fat, adipose tissue. Two types, unilocular and multilocular. It refers to the appearance of or the packaging of the fat, the lipid, within the adipose cell. So that within a unilocular, also known as a white fat cell, there is one very large fat lipid globule in it. In the multilocular cell, there are many smaller globules. Also, this is a much more active type of tissue. It's often called brown fat. It has a very high content of mitochondria in it. Both of these are going to come from or be derived from mesenchyme. This type of fat, brown fat, is prominent during birth, honestly, during early childhood, when children have a very low surface area, so to speak, and to fat ratio, and the brown color is given to it by the fact that there's a lot of cytochrome oxidase in it and within the mitochondria. Now, what happens is there is a protein within these fat cells that takes the proton gradient, you know about OXPHOS and all that, and the proton gradient, okay, which uncouples the proton gradient from oxidative phosphorylation and ATP production. So that if you don't have that proton gradient and you don't get all of that ATP production, instead you have less ATP produced, but what will be produced is heat, okay, in place of it. So you don't get all that energy, but you get heat. So that coupling protein is also called thermogenin. So this helps to maintain body temperature in infants. It's also something, it is the way that hibernating animals stay warm during the winter. So bears stock up right? And what happens then is that they undergo something called non-shivering thermogenesis. This uncoupling protein is producing heat, non-shivering meaning heat, keeping the body warm. Okay. Okay, so that's multilocular brown fat. It's a very much more active type of tissue than the unilocular fat. All right, all from mesenchyme, and of course this is the major site for triglyceride storage, and it is found throughout the body, insulating and contouring. Right, the hypodermis, the subcutaneous of the skin. So the superficial fascia. Okay, those are all synonymous. Superficial fascia, when you're in there in the growth lab, you're cutting through skin and you're cutting through superficial fascia, which is going to have varying amounts of fat in it. Sometimes related to where you are in the body, other times just related to the dietary condition of the person who produced that fat. Okay. It cushions organs, a fair amount of fat around the heart for cushioning, but not too much fat, because that's not good either, around the kidneys, okay? A fair amount of fat. And then on the palmar and plantar surfaces of the extremities, okay, of the distal extremities, where there are fat pads. Okay? In fact, one way of measuring fat content in the body, those scales, where you're saying they're measuring the fat content in the fat pad in the foot, in the sole of the foot. Okay. It can regulate energy metabolism through paracrine and endocrine factors. Okay. Paracrine factors being those that act on surrounding tissues, endocrine acting at a distance through the blood system. Okay. So what else does it do? Well, it produces a satiety factor called leptin, which is involved in energy homeostasis. It's involved in production of angiotensinogen and the conversion of steroid hormones, and it is a source of multipotent stem cells. Okay, so that's sort of the big thing now. There is a company from the university linked with the University of Arizona in Tucson called Adicyte, which will store your fat for you so that when you need it, you will have a source of stem cells. They will be your own stem cells. And I like this, it's great. So, okay, and also actually at the American Heart Association meetings last month, it was reported by a group out of the bioengineering department in the University of Oklahoma that they were able to get stem cells from fat aspirates, and they put them into culture and were able to, first of all, produce vascular endothelial cells, and then rolled them to produce blood vessels. Now, small blood vessels, you hoping to use those as bypasses for patients that might not be able to go through the type of surgery where you have to take blood vessels from the femoral region or the other region to make blood vessels. So there's a lot of potential in that area. Stem cells is something, of course, you're going to hear about probably in every one of these lectures as we tell you, as we have to revise what we've told you in the past, saying, nah, that cell doesn't regenerate, those tissues don't regenerate. Well, now we know that there are things around that will help them regenerate. But in particular, though, adipocytes and the stem cells that are probably right there peripherally within them have gotten to be a big thing. So I think I'm going to stop lecturing and I'm going to start opening up a liposuction company. Okay. So in the growth lab, you're going to go into the growth lab in a few weeks, and you're going to be cutting through epithelium and connective tissue. And so what then do you see? This is a picture of thin skin, And the first thing you're going to do when you're in the growth lab is you are going to cut through thin skin because you're going to cut through the skin of the back. You always start on the back, okay? Always the best place to start. All right. And you will see that the skin itself is going to have a consistency or a look something very much like an orange peel, where there'll be a dark band at the top. You know, think about an orange peel. It's orange and then it's white where the pulp is. Lemon peel, yellow pulp. Okay, so like citrus peel. It'll have a dark band at the top, which is the epidermis or the epithelium of the skin. And then you'll go through a very dense, kind of compacted, creamy white, maybe yellowy sort of region of compacted tissue, which is the dermis, which is the dense, irregular connective tissue, or the CTP. Okay? When you get beyond that, you'll pop through and you'll get into a region that might have varying amounts of fat, the subcutaneous tissue, the superficial fascia. That's where you're going to find things like cutaneous nerves, the cutaneous blood vessels, okay? And then you get a little bit deeper in that you will get down to the deep fascia and the muscles and those good things that you're going to be looking for. But to get to those muscles, you're going to see that they too are going to be in a deep fascia, another connective tissue covering. All right? So as you go into the growth lab and you're cutting through these organs and cutting through these tissues, try to equate it a little bit with what you're seeing here in these labs. Now, we have till 4:30. I don't plan on taking 4:30, but if you like, I will go through a couple of the web slides for you to show you how to approach them. Okay? So let me stretch for a minute while I get this set up. Okay? All right. Okay, how do I do this? Okay. Oh, let's make sure I can actually open this up, because sometimes these things do wild things to me. Don't tell me you're not going to open. Come on. Ah, and it's going to open. Okay. Now, what I did was, and it's a good thing to start right now to get ready for the exam, okay, and studying. I went through the 3 labs, the epithelium, mammary, and adipose lab, and I wrote down the slide numbers for the web slides and what they were for each lab, okay? It's epithelium, connective, and adipose. And as I did that, I noticed that it's in both labs. And there are a number of them that go into both labs, okay? And you're going to find that you will come back to this in the muscle lab and in the nerve lab. So, pardon me?
Sorry, what does that say?
I'm sorry, it says jejunum. I'm sorry. You are really supposed to worry about what the word was. Okay, but the deal is that once you've gone through all these tissues, yes, you're going to know all of the specifics, but the deal is that you have to start putting them together. And it will save you a lot of time if you know that, hey, I can take this jejunum slide and I can look at it, and I should be able to look for and find a simple columnar epithelium with microvilli and terminal bars. I should be able to find a 2-layered smooth muscle wall with muscle running in opposite directions. I should be able to find a nerve plexus, plasma cells, whatever, okay? And you do that, and you have now cut down your space of time drastically, and you also are preparing yourself for the organ systems that you're going to be getting into. So if you start now, it doesn't take that long to do it, okay? So that's my tip. You don't have to do this. You can do it any way you want to. Okay. So I'm starting here with where we were before, okay? Look, this is from the mammary gland, and this is not exactly the mammary gland picture that I showed you because, there we go. You can see that there's not a lot of connective tissue in here, okay? So the picture of the mammary gland that I showed you that had that connective tissue all of that connective tissue has now been filled up with secretory units. But what we can see over here is the fact that we have an epithelium. And that epithelium, invariably, first of all, it'll be near the surface. It'll be at a lumen, okay? It will stain darker because the cells always are much more active than those inert fibers that are laying around there in the connective tissue. And there's a region of connective tissue under here. What we're looking at here is, anyone know? It's dense irregular connective tissue, but do you have any idea what this structure is? We're in the mammary gland. Ladies? Nipple, areola, and the gland. Okay? We're going to go, okay. We'll look at it again when we do mammary gland. Okay, we're going to go back to epithelium, and we'll start with epithelium. Get dizzy looking at this. Okay, here we go. Okay, so in terms then of the epithelium, Dr. Becker has kind of he actually went through and he took out all of the glass slide references, and everything is cross-referenced to figures within R&P, and these should all be from the 6th edition, so you shouldn't have any problem with that. But since we talked about it and since we had it there, we'll look at the jejunum, okay? So we're looking at something that is, so you can move it around. Left. Okay. Here we have a very smooth, thick band. Tissue in here that looks not very cellular, so perhaps CT, connective tissue. And then something in here that has a lot of finger-like projections, okay? You have a book that you can follow, all right, but this is from the small intestine. This is the lumen of the small intestine. It's a tubular structure, okay? The jejunum is the second portion of the small intestine, stomach, duodenum, jejunum, okay? And this band here is the muscle wall, 2 layers, and the epithelium is going to be on these villi, which are folds within the mucous wall that help to increase surface area. Okay? So we have these big, huge pleated or plicas, and then all of these little villi, and then on top of those are going to be the epithelium. So you do well, I'm using Mac here, so you do a Control-Command-Click, and you get a magnification. Now, you have to watch the green area here if you want to go up in mag, okay? So note that here, let's see if I can do this. Yeah, okay. Here is the smooth muscle band. And when you bring it up in power, you'll see that there are muscles running in 2 different directions. Here is a lot of connective tissue in here, but over here, you can see that you have a line, a dark line, covering each of these villi. So look at how we've expanded the surface area. When you get into these villi, come on, dude. There we go. Aha. You now have that simple columnar epithelium that we looked at before. Okay. See if we can find a good area here. So this is a villus here. Here is connective tissue in the core. Here are the nuclei of these tall columnar cells. And up here is the border, the striated border, which are the microvilli, right? Microvilli are ultrastructural structures on a cell, whereas villi are these folds within the mucosa. All right. So where then would you find terminal bars? Huh? Here? In here? Here? Okay, right, because it's going to be, this is lumen, right? All of these are projections into the lumen. Okay, so that's your smooth, your simple columnar, simple epithelium. These are very active cells, and we're not dealing with a lot of friction here. In the jejunum, we're dealing with absorption. This is the main absorption site, okay? You might find within here some plasma cells, perhaps, or some, let's see what we got. If you're looking for things like plasma cells, eosinophils, lymphocytes, things that might come in to the, oh, I wish those people on the east side would get off the blackboard. Okay. All right. We're dealing with mast cells and eosinophils in here and plasma cells right here. Another plasma cell. Okay. You can bring this power up, but when you're in, you know this is how you get your orientation. You look to see what kind of an organ you're looking at, whether it's got a muscular wall. Find the lumen. When you find the lumen, you're going to find the epithelium. You also, epithelium in blood vessels. Okay? But where are you going to find the blood vessels? Down in the connective tissue. These are bigger blood vessels. You might find smaller ones up in here. Okay? But in the blood vessel, you want to have diffusion as you get things in and out of the tissues. You're carrying things, and you only have a simple squamous epithelium or an endothelium. All right? So, do you want to say anything else here? Can we look at a different one?
I have a question.
Huh?
I have a question.
Yeah.
How are we supposed to know how we look at things to the landing? You're saying it's columnar epithelium? I don't know why, but I can't see how it's columnar.
Okay. You can't see this? Okay.
Are we supposed to?
Can you see that can you see that these cells are all lined up and that they're very closely opposed to each other? Okay? Can you see in here this region where you have cells that really aren't in any specific pattern? All right? Here you see that you have all these nuclei lined up. This cell then it's a very tall, skinny cell. Every nucleus represents a cell. If it's taller than it is wide, it's a columnar cell. But in this particular kind of epithelium and in this region, they tend to maintain that shape. But sometimes when you get into other tissues, say in the thyroid gland, some other places, the cell shape can change from cuboidal to columnar depending on the activity of the cell. These always remain columnar, just because they have the business end is up here where they're absorbing and they're doing all sorts of processing as they're bringing in the digested products into the cell and then out into the connective tissue. These cells here, big and kind of clear. Any idea, folks? Looks like it's spitting something out onto the surface. Goblet cell, one of those mucus cells. Yes, ma'am.
During the exam, are the images, because they're digitized, are they going to be at the magnification? Or can we move and change the magnification?
You know, I do not know if they will give you, if they want you, this has always been a general rule, even with glass slides. If we wanted you to identify something small, like a plasma cell, we would give you a fixed image, okay? If we want you to be able to identify, say, a tissue or something within an organ, you have to be able to maneuver. Now, you're the first full class that's going to be doing this. I have no idea. And, you know, but I have been told, as I tried to get my lecture up today, that this will have nothing to do with Blackboard, so you won't be dependent on whether the server for Blackboard is screwed up or not. So, okay. I want to do one other one for you just to give you an idea, and that is, if I can find it, the trachea. Yeah, here we go. This is a slide that used to cause a lot of problems in the lab when it was a glass slide, because it said that there was trachea and esophagus. It didn't always say there was trachea and esophagus on the same slide. It said that you should look for stratified squamous epithelium, and some people only had trachea. All right, so this is a slide that's taken, it's a cross section through the neck, okay? And if you feel in the front of your neck, you can feel cartilage, right? The cartilage rings of the trachea, okay? And sitting behind the trachea is the esophagus, all right? So this is probably taken from a mouse or something like that, since it's a very small section, okay? Now, what you have then is you have the trachea, you have the esophagus, and up in here, you'll find that you have skeletal muscles, the strap muscles, okay, that run between the hyoid bone and the thyroid cartilage. All right, two different kinds of epithelia, and you can look for both of them. The trachea is part of the respiratory tract. What type of specialization would you expect to find on the apical membrane? Very good, all right. And it is respiratory epithelium, right? And so it gets classified as pseudostratified epithelium, ciliated. The esophagus basically is moving a bolus of food down. And it's something I didn't go through, but what kind of an epithelium do you think you would have if you had to move a bolus of food down? Huh? A stratified squamous epithelium, and also one that would produce some sort of mucus to help to keep that moving down, okay? So which one do you want to look at first? Esophagus, okay. All right, so that's going to be this one here, okay? It's going, both of them will have smooth muscle in their walls, involuntary muscle. Here's the lumen of the esophagus here. Here is the muscular wall of the esophagus, okay? Lumen of the trachea and the wall of the trachea with the cartilage that you'll be looking at. And then all around here is fat with blood vessels, nerves in it, and there's going to be a cervical fascia around here setting this up, closing this off, okay? So we'll do this one first. Okay, so here we have the lumen. Here's the connective tissue under it. You've already looked at the low-powered view and you've gotten your orientation. And here is the demarcation where you would have the basal lamina in this region. Connective tissue, fat cells, not big globs of isolated fat tissue, but fat cells, blood vessels, lined by simple squamous. And this is now this dark region where all of these nuclei, and layer upon layer, then makes it a stratified squamous epithelium, all right? And these cells down here are staining darker. Why? Why do these down here stain darker? If the blood supply is here, where are the most active cells going to be? At the bottom. The epithelium grows from the bottom up, okay? So these are the most active cells. They're going to have the most organelles in them, and that's why these cells always stain the darkest in a stratified epithelium, the ones that are nearest the basal lamina. In terms of this esophagus, this is from a very high up portion of the esophagus, near the trachea, as opposed to down here in the thoracic cavity. And what you're going to find is, you'll learn next week, that this is skeletal muscle, okay? Yep. And you'll be able to look at that. I should have done this so I could see where I'm moving here, okay? I'm going through lots of fat, huh? And now you'll be able to look at that and compare it to the smooth muscle that'll be around here. Dr. Becker will be talking about cartilage, hyaline cartilage, next week. Fat, 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 fat. What kind of fat? Unilocular. Okay, good. And now we're into not a stratified squamous epithelium, but one that looks like it has something still attached to the luminal surface, right? Let's bring it up. And you can see that you have, this is tricky, all right, because you have a lot of nuclei that are at different levels, but you really don't have a lot of layers of cells. These are tall, columnar cells. And you have dark regions right here under these projections. So these are your cilia. Looks like there still might be some mucus and dust particles on top. And this is a pseudostratified epithelium. I'll bring it up again. It's easier to see it on EM that it's pseudostratified. You basically, on light microscopy, you have to know the rest of the organ and just say, okay, fine. If I'm in the male reproductive tract in the epididymis, I've got pseudostratified epithelium. And if I'm here in gee, these are nice cilia, aren't they? Pretty. Those really are nice. And here are the basal bodies. Okay. But you're not going to see everything, right? You know that you have basal bodies there, but you're not going to see that basal foot and the rootlet and everything else, right? And then you get down in here and you've got your connective tissue. Okay? You move out through all the connective tissue and you'll get back to at some point. The cartilage that Dr. Becker will be talking about. Okay, so basically, I really don't want, if you want me to go through more, I will, but that's how you do it. You take a low-powered view, get your bearings, look for a lumen, look for the surface, look for the dark compacted tissue, find the stuff that looks looser, and go from there.